Let's go. The diagram below shows the photoelectric effect. State the meaning of photoelectric effect. There are 4 points here. First, the photoelectric effect is the emission of electrons from where? From the surface of a metal. And when is this? When illuminated with a beam of light, but not just any light. The light has to be of a certain frequency. It has to be above the threshold frequency. An incident light of wavelength 675 nanometer is shined on the surface of the metal. Given that the work function of the metal is 3.14 times 10 to the power of minus 19 joules. So they've given you C and H, the value of the constants. Calculate the energy of one photon of the incident light. So when we go with energy of photon, it is E is equals to HF. This is the base formula. When we don't have frequency, in this case we have wavelength instead of frequency, then we use F is equals to C over lambda. You substitute this in and you will get E is equals to HC over lambda. Let's substitute our values in. E will be equals to H 6.63 times 10 to the power negative 34. C, which is 3.00 times 10 to the power 8 over lambda, 675 nanometers. We should substitute everything in SI units here for our answer to be in joules. So from nanometer, we need to convert to meter times 10 to the power of negative 9. And the answer is 2.95 times 10 to the power of negative 19 joules. Our answer will be in joules if we convert everything to SI unit when we substitute into the equation. State whether the photoelectric effect would occur. Explain your answer. So when we decide whether or not the photoelectric effect would occur, we have to check the work function and the energy of the photon, and we have to compare the two. The work function is 3.14 and the energy of the photon is 2.95 times 10 to the power of 19. So in this case, you can see the energy of the photon is less than the work function. What is the work function again? It is the minimum energy required to emit the photoelectrons for the photoelectric effect to occur. So the answer in this case is no. It will not occur because the energy of the photon is less than the work function of the metal. Another beam of light with frequency 1.34 times 10 to the power of 15 Hz was shined on the metal. Calculate the maximum kinetic energy in joules of the photoelectrons released. Now, in this case, whenever we have maximum kinetic energy of electron during the photoelectric effect, then we use the photoelectric equation, which is E is equals to W, work function, plus maximum kinetic energy. This is the formula used when you see maximum kinetic energy of photoelectron. And so we rearrange this because we want the kinetic energy. We make this the subject of the equation. Ke max will be equals to E minus W. And so we substitute E as HF minus W. In this case, we already have the work function, so there's no need to find it. Now we just have to substitute the values. So the energy of the photon now will be 6.63 times 10 to the power negative 34. This is Planck's constant times the frequency, which is 1.34 times 10 to the power 15 minus the work function. So it is the same metal, so it has the same work function. The work function was 3.14 times 10 to the power of negative 19. So 3.14 times 10 to the power of negative 19. And our answer will be 5.74 times 10 to the power of negative 19 joules. Question 2. A metal has a work function of 2.86 electron volts. Calculate the maximum kinetic energy in electron volts of the photoelectron release when a light of wavelength 326 nanometers is shined on it. So in this case, we are going to deal with energies in electron volts instead of joules. When we are dealing with maximum kinetic energy, the formula remains the same. That is, E, energy of photon, is equals to work function of the metal plus the maximum kinetic energy of the photoelectron. This is by conservation of energy. So calculate the max Ke. Again, Ke max will equals to E minus W. So in this case, E will be, since we have wavelength, we don't use HF, we use HC over lambda minus W. So now let's substitute the values. So H again 6.63 Planck's constant times 10 to the power negative 34 times 3.00 times 10 to the power 8 divided by the wavelength. The wavelength here is 326. So 326 nanometers times 10 to the power of negative 9. Now here, this answer, the value that we get from this calculation will be in joules. However, we want to find our answer in electron volts, and the work function is already given in electron volts. So therefore, we need to convert this value into electron volts. And so we can use the conversion factor here. 1 electron volt equals to 1.6 times 10 to the power of negative 19 joules. When we are going from joules to electron volts, we need to divide this value. So in order to convert this to electron volts, it's currently in joules, we have to divide the whole thing, the answer that we get, divide it by 1.6 times 10 to the power of negative 19. And now this answer, this new answer, the whole thing here will be in electron volts. And now we can subtract the answer in electron volts as well. So minus 2.86. Now they are the same unit, so we can perform this operation. Alternatively, you could have converted the work function to joules and then in the end convert back to electron volts, but that's just a longer way, but it's not wrong. So the answer here is equals to 0.95 electron volts. Question 3. A yellow light bulb emits light at a wavelength of 580 nanometers at a power of 40 watts. Calculate the number of photons emitted in 6 seconds. So when we deal with power and number of photons, then you must remember the formula. P is equals to NHF. So in this case, we don't have F. Instead, we have the wavelength. And as usual, all we have to do is substitute frequency with C over lambda. So you will get NHC over lambda. And now we are ready to find the number of photons emitted. So the number of photons emitted in this equation does not exist. This N here is actually the number of photons emitted per unit time, per second. So let's find that first. Let's find N first. So we substitute our values inside. P is 40. 40 equals to N. First we want to find the number of photons emitted per second. And then H, so times 6.63 times 10 to the power negative 34. And then C, which is 3.00 times 10 to the power of 8. And then we have to divide with lambda. So lambda will be 580 nanometers. 580 times 10 to the power of negative 9. Okay. So now we can rearrange to find N. N will be equals to 40 multiplied by 580 times 10 to the power of negative 9. Divided by 6.63 times 10 to the power of negative 34 times 3.00 times 10 to the power of 8. So now we can find the value of N, which is 1.17 times 10 to the power of 20 photons per second. So this is the number of photons emitted per second. The question wants you to find the number of photons emitted in 6 seconds. And so we have to multiply this with 6. So the number of photons emitted in 6 seconds equals to this value 1.17 times 10 to the power of 20 multiplied by 6. And so the answer that we would get is 7.00 times 10 to the power of 20 photons. Remember not to give your answer in only one significant figure. Question 4. State how to determine the value of Planck's constant from a graph of activation voltage VA against frequency of emitted light F. This is from the experiment to determine Planck's constant. And so for this experiment, you need to remember one equation. That is the conservation of energy, the electrical energy of the electron, EV is equals to the energy of the photon, which is HF. This voltage here is the activation voltage. And so when we rearrange this equation, because we are plotting VA against F, so VA equals to, we apply linear law, H over E F. So in this way, when you plot VA against F, we get H over E as the gradient. And so gradient equals to H over E. And how do we find the value of Planck's constant? Value of Planck constant will be the gradient of the graph times E, the charge of one electron. Number 5. We want to determine the value of Planck's constant again, but this time we have a graph of VA against 1 over lambda. So in this case, we go back to the same equation first, that is EV equals to HF. This is the activation voltage. Now in this case, we are plotting against 1 over lambda, and so we need to convert F to equals to EVA will be equals to HC over lambda. And so now we apply linear law. VA equals to, we divide the whole thing by E, so you get HC over E multiplied with 1 over lambda. So in this case, you can see, if you plot VA against 1 over lambda, then HC over E is the gradient. And therefore, gradient equals to, the gradient of the graph would equals to HC over E. H will be equals to the gradient times E divided by C. 6. A man-made satellite orbits the Earth at a height of 438 kilometers. Calculate the value of the gravitational acceleration of the satellite. So here the formula for gravitational acceleration G is equals to Gm over r squared. So now the question is, what is this m? This is the mass of the object that is exerting the gravitational force that causes the gravitational acceleration. So it is not the mass of the satellite. The satellite is not the one that is exerting the gravity on itself, whereas it is the Earth that is exerting the gravity on the satellite. So the mass here will be mass of Earth. So this will be equals to G 6.67 times 10 to the power of negative 11 times the mass of the Earth, which is 5.97 times 10 to the power of 24. And then these values are given. And then we have to divide by r squared. So now the question is, what is r? R is not radius. R is the distance between the two centers of mass of the objects. Let's sketch a diagram here. So we have the Earth, and then we have the satellite orbiting the Earth. So let's just put a dot here. Okay, this is the satellite that's orbiting the Earth. Now where is r? So r will be the distance from the center all the way to the center of the satellite. But this distance here between the center and the surface of the satellite is negligible. It's very tiny compared to the whole overall distance. And so we can ignore that. But here, what is this? This is the radius of the Earth. And this side, we have the height of the satellite. So what is r actually? R is the radius of the Earth plus the height of the satellite. And so this is what we're going to substitute inside here. So this will be over radius of the Earth, also given 6.37 times 10 to the power of 6, plus height of satellite. Height of satellite is 438 kilometers. Please remember to use your SI units. So this is 438 times 10 to the power of 3 squared. And so the value here is 8.59 meter per second square. 7. Satellite P takes 15 months to orbit a planet. If another satellite Q is located 3 times further away from the planet compared to P, calculate how long it will take for the satellite to orbit the planet. So here we are looking at orbital period and the distance from the planet. So we are going to look at the relationship between T and R. Here we are going to apply Kepler's third law, that is the law of periods. And the law of periods states that the square of the period of the orbit is directly proportional to the cube of the distance between the two centers of the objects. So we're going to use this relationship in this question. And so first we say that T square is equals to constant multiplied by r cube, and so we know that T square over r cube equals to constant. The ratio of the period square over r cube equals to constant. From this, we can do T1 square over R1 cube is equals to T2 square over R2 cube. And so this is what we're going to use to solve. Let's substitute our values inside. Since we want to find the period of satellite Q, let's make this 1 and let's make satellite P2. Now the period of Q, orbital period of Q square over the distance between the center of Q and the center of the planet Q. So they say that it is 3 times further than P. So let's make the distance between the center of P and the center of the planet R. So this will be 3R. So 3R cube, because we don't have the actual value, but we don't need the actual value. And here 2, let's use satellite P. So the period is 15 months. You don't have to convert to SI units here. As long as the units on the left and the right are the same, when we use this method, it is fine. So the R here will be just R cube. And so now we can, let's expand the brackets first. So we have T square over 3 cube R cube equals to 15 square over R cube. So you can see what's going to happen here. Multiply R cube on both sides and we have eliminated R cube. And so now we will get T square equals to 3 cube times 15 square, and T will be equals to square root of 3 cube times 15 square. Alright, so the answer here will be 77.9 months. We use the same units as the period earlier. 8. The escape velocity of the Earth is 11.2 kilometers per hour. Calculate the escape velocity of a planet that has twice the radius of the Earth and 3 times the mass of the Earth. So again, we are going to use relation here. The formula for escape velocity is V is equals to square root of 2gm over R. So once again, R is the distance between the two centers of mass. So here we have the relation. We are looking at a change in radius and mass, and we are looking to find the new escape velocity. And so the 3 variables here are V, M and R. 2 and G are constants. So we can write this as V is the square root of M and R, because 2 and G are constants. So now we can make this into an equation. That is, we add the constant of proportionality K. V is equals to K square root M over R. And so now we can rearrange this. We make K the subject. K is equals to V square root R over M. All we want to find is what is equals to the constant. We can apply this. We can use this relation as V1 square root R1 over M1 equals to V2 square root R2 over M2. Since we want to find the escape velocity of the new planet, let's take the new planet as 1. So the new planet is 1, and let's put Earth as 2. So the escape velocity of the planet is what we want to find. So we have V1 here. Square root of, what is the radius of the new planet? The radius of the new planet is twice the radius of the Earth. So let's put that as 2R. R being the radius of the Earth. And then it is 3 times the mass of the Earth. So let's put that as 3m. M being the mass of the Earth. So this is equals to 2 is Earth. So escape velocity of Earth is 11.2. Remember, this is in kilometers per hour, but it doesn't matter because we are using relations. Square root of R over M. This will be equals to V1 square root 2 over 3 square root R over M. What we are doing is we are separating this multiple inside the square root. Is equals to 11.2 square root of R over M. Now the reason we do this is so that we can divide by square root R over M on both sides and eliminate it from the equation. And so V1 will be equals to 11.2 times square root 3 over 2, reciprocal. From the left side to the right side we multiply the reciprocal. And so the answer here is 13.7 kilometers per hour. The unit must be the same as what we substituted on the other side. Number 9. A geostationary satellite K of mass 1126 kg is placed at a distance of 6.41 times 10 to the power 6 meter from the center of the Earth. So they've given you a few constants here. State the meaning of geostationary satellite and list its characteristics. So a geostationary satellite is a special satellite that moves in the geostationary orbit. As long as it moves along that orbit, it is a geostationary satellite. And its characteristics are, it has an orbital period of 24 hours, which is the same as the amount of time it takes for the Earth to make one complete rotation. And it moves around the Earth in the same direction as the rotation of the Earth's axis. It moves together with the rotation, the same direction as the rotation of the Earth on its axis. And it is always above the same geographical location on Earth. If it is above, let's say it's above my house, then it will always be above my house, no matter how the Earth spins. Calculate the linear speed of satellite K. The formula for linear speed, V is equals to square root of Gm over R. So now we just have to substitute the values. This is square root of 6.67 times 10 to the power of negative 11 multiplied by, now what value of m should we substitute here? Remember, this m is always the mass of the object that is exerting the force of gravity, not the object that is experiencing the force of gravity. So this would be exerted by the Earth. So we do the mass of the Earth here, which is 5.97 times 10 to the power of 24 divided by the distance between the two centers. So the distance between the two centers is also given to you. That is this value, 6.41 times 10 to the power of 6. So divided by 6.41 times 10 to the power of 6. And the answer is 7882 meters per second. Calculate the force of gravity exerted on satellite K by the Earth. The force of gravity here acts as, when we have the Earth and we have the satellite orbiting around the Earth, then the force of gravity is the force that acts towards the center of this circular motion and causes the satellite to move in circular motion. Therefore, the force of gravity is actually the centripetal force in this case. And so, we can simply use the formula for centripetal force. You could use the formula for gravity, Gmm over r square, but in this case, that's not necessary. We can just use mv square over r. So, this m, when we use mv square over r, this m is the mass of the object that is experiencing the force, that is experiencing the centripetal force, which is the mass of the satellite. And so, this will be equals to 1126, the mass of the satellite, times v square, what we got earlier, that is 7882 square, over the distance, the same distance, that is 6.41 times 10 to the power of 6. And so the answer here is 10913 newtons. Another satellite L orbits the Earth at a greater distance from the Earth compared to K. Compare the linear speed of satellite K and L and explain your answer. In this situation, we need to use the relation between the linear speed and the distance from the Earth. And so, we can write our formula, linear speed equals to square root of Gm over R. G and M are constants in this situation. So, we get V is inversely proportional to the square root of the distance between the two centers of mass. And therefore, if the satellite is at a greater distance and orbiting the Earth, then the linear speed will be lower. The linear speed of satellite L is lower than satellite K. Why? The linear speed of the satellite is inversely proportional to the square root of the distance between the two centers of mass. A space junk of mass 259 kg is found to be 3.1 km from satellite K. Calculate the gravitational force exerted on satellite K by the space junk. Now, it doesn't matter whether it is the gravitational force exerted on the space junk by K or on K by the space junk, the magnitude is the same. And the formula for this, we use Newton's universal law of gravitation, Gmm over r squared. Once again, r is the distance between the two centers of mass. So, G is 6.67 times 10 to the power of negative 11. M is the mass of either object. So here the mass of the two objects, let's take the space junk, 259, and then we need the mass of satellite K. From the question we know that it is 1126, and this we need to divide by the distance between the two centers of mass square, which is 3.1 km. So this is 3.1. So kilometers, we need to use SI unit here, times 10 to the power of 3 squared. So the answer that you will get here is 2.02 times 10 to the power of negative 12 newtons. I hope this has helped, guys. If it has, please do me a favor and hit the like button. If you need to do revision on more topics, I will leave links to the videos in the description below. All the best, guys.